Hi everybody. This section is going to be 10.2 and the section is called Calculus with Parametric Curves. Okay, so I want us to suppose that we have a parametric curve. So suppose we have a parametric curve. Remember, parametric curves follow the form x is some function of t and y is also some function of t. And also, I want us to suppose that y is a differentiable function of x. Now remember, that might sound like an intimidating statement, but all that means is that the curve is smooth. It doesn't have any sharp edges, so it does have tangent lines everywhere. So how do we find dy dx? So our goal right now is we want dy dx, which, remember, this is just the slope of tangent line. The meaning does not change. The only difference here is that we do not have y as a function of x. We actually are given parametric equations. So the key here is to use the chain rule. So by the chain rule, if you were to do dy dt, that's the derivative of y with respect to t, is equal to dy dx times dx dt, right? This is the chain rule. Since y is a function of x, we're assuming that, right? We're assuming that y is a differentiable function of x. So, what does this mean? This means that if we solve for dy dx here, right, we're trying to get that guy by itself, we just have to divide both sides by dx dt. And what this gives us is dy dx is equal to dy dt over dx dt. Of course, this is only possible if dx dt is not 0. Okay? So there you go. We just got our derivative, okay? This is how we find dy dx in a parametric equation. You find dy dt, you find dx dt, and then you divide them. Okay? Now, what about the second derivative of y with respect to x? Okay, to do that, I want to use the last formula, right? So the second derivative of y with respect to x is going to be the derivative of dy dx with respect to x, right? So what we need to do then is we just need to apply the same formula as before, right? And so what are we going to get? This is going to be the derivative of the first derivative with respect to t over dx dt. So this is going to be the formula that gives us our first derivative, right? Notice that this is just our last formula, except we're replacing the y in the formula with dy dx since we want the second derivative. Okay, so this is how you find the second derivative. Now, what are we going to do with this information? So I want us to recall some facts about tangents, right? Tangent lines and things like that. So let's recall some stuff. A tangent line is horizontal This is all stuff we learned in Calc 1, okay? It's horizontal if dy dx is equal to 0. That's something that we learn in Calc 1. Also, a tangent line is vertical if the limit as x goes to a from the left or the right of dy dx is equal to plus or minus infinity, okay? So either infinity, that's what it means for a tangent line to be vertical, and this is what it means for a tangent line to be horizontal. But since we have our new formula now for dy dx, dy dx, remember, is equal to dy dt divided by dx dt. This means that the tangent line is horizontal if, so let's think, when does this fraction equal 0? It's equal to 0 when the numerator is 0, right? And the denominator is not. So it's going to be horizontal if dy dt is 0 and dx dt is not 0. It's going to be vertical if, well, we're still going to need to do a limit here, right? So this is going to be if the limit as x goes to a of we still do care about where that thing is plus or minus infinity, but you want to check, the way you're going to find this guy is you're going to check values of a where you get something undefined. In other words, where dx dt is equal to 0. Okay? Wherever dx dt is 0, this actually means that your slope is undefined, and so those might be vertical tangent lines. Let me do one more note that helps, okay? Just as a recall. When calculating a limit, okay, if you ever have a non-zero number on top and you get something that approaches 0 on the bottom, this always goes to plus or minus infinity. Okay, so this is all you really have to check, okay? All right, so we're going to do a nice example here. This is going to be a really involved example, but we're going to analyze a parametric curve using what we know and using these new formulas, okay? So, example 1. A curve C is defined by the parametric equations x equals t squared and y equals t cubed minus 3t. So we have multiple steps here. I'm going to do this step by step. So part A is to show that C has two tangents at 3, 0 and find their equations. So let me do part A first, and then I'll just write each part individually, okay? Because this is actually a 4-part question. It's going to be pretty long, okay? So first we're going to show that C has two tangents at 3, 0, and we're going to find their equations. This is already kind of weird. How can something have two tangent lines at the same point? Well, the idea is that the curve must loop on itself, right? Whatever it's doing, we know that at some point it's got to cross itself twice because it's going to have two different tangent lines there. Okay, so let's see how this works. First, we're going to find the derivative, okay? So let's go to the next page here. So what is dy dx going to be? Well, remember that dy dx is just dy dt divided by dx dt. So what's the derivative of y with respect to t? Well, remember the equation was y is equal to t cubed minus 3t. So its derivative is 3t squared minus 3. And for dx dt, the derivative is 2t. Okay? So what are we doing here? We need to see where this has, we need to show that this has two tangent lines at 3, 0. So first, let's find the t that corresponds to 3, 0. Now, of course, every value of t in the original parametric curve corresponds to corresponds to an x and a y, right? And this is x and y. So if we were to do a table here, here's what we're doing. What we're saying is that when x and y are 3 and 0, what would t be? Well, the trick is to look at the original equations, right? If we know that x is equal to t squared, this implies that 3 is equal to t squared. And if y is equal to t cubed minus 3t, this implies that 0 is equal to t cubed minus 3t. And so we need to actually solve this. We need a t value that works for both of these equations. What do we get? Well, this top guy gives us t is equal to plus or minus root 3. This guy actually gives us three numbers, right? T is equal to, oh, sorry, this should be a 3. Sorry, typo here. So this is t minus root 3, t plus root 3. In other words, t is 0 and plus or minus root 3. So of course, the only values that work for both are plus or minus root 3. You don't want t equals 0 because t equals 0 does lead to the correct y value, but not the correct x value, okay? Because if you plug it in the x equation, you just get 0. That's 0, 0. It's not the point we want. So here we go. This means that at root 3 and at negative root 3 of t values, that corresponds to an x and y. Now, how would we actually figure out what the tangent line is? Because we remember we're trying to show that C has two tangent lines at 3, 0, and we're trying to find their equation. So here's the idea. The idea is that it crosses 3, 0 twice. First when t is equal to negative root 3, and then when t is equal to root 3. So let's do each one at a time. What's dy dx? Let me back up here. I'm going to do this on the next page. So first, what is dy dx at t equals, let's start with negative root 3. This means we're going to plug negative root 3 into our dy dx equation. So what do we get? It's 3 times root 3, negative root 3 squared minus 3 over 2 times negative root 3. Over 2 times. So what do we get here? Let's see, 3 times 3 is 9, minus 3 is 6 on the top, and on the bottom we get it over negative 2 root 3. which is negative 3 over root 3, which is negative root 3, right? Anything divided by its radical just gives you the radical. Okay, so we got the slope of the tangent line for the first one, right? So what is tangent line number 1? Well, we know that this is the slope, right? This guy right here is the slope, and we know it goes through 3, 0. So that means that the tangent line number 1 is going to be y minus 0 is equal to m times x minus 3. Okay, because it goes through 3, 0, and it has slope negative root 3. Okay, what about tangent line number 2? Oops, I shouldn't write this yet because we still need to find dy dx there, right? So what is dy dx when t is positive root 3? So this is going to equal 3 times root 3 squared minus 3 over 2 times root 3, which is equal to, still 6 on the top, but this time over 2 root 3. This is just 3 over root 3, which is root 3. And so we found our second tangent line. Tangent line number 2 is y minus 0 is equal to root 3 times x minus 3. Well, let me be consistent. I only circled that last time. Okay. So we're done with part A, right? Part A wanted us to show that there were 2 tangent lines, and we found both of their equations, right? Okay, let's move on to the next part. Part B. Part B says we're going to find the points on the curve where the tangent is horizontal and vertical. Or let me just say or vertical. Okay, so remember we had our derivative, right? So our derivative was 3t squared minus 3 over 2t, right? So this was our dy dx. So if I were to set the numerator and denominator equal to 0, remember we already got that actually, right? We got those values in the last part. Okay. Oh, actually, did we get that in the last part? No, I think we haven't done this part yet, right? So what I'm going to do is I'm going to find where both parts are equal to 0, right? So if we do 3t squared minus 3 is equal to 0, this is the same as t squared equals 1, which is the same as t equals plus or minus 1. If I do 2t equals 0, this is the same as t equaling 0. So, where are my horizontal tangent lines? Remember, horizontal tangent lines occur where we get 0 here for dy dx. This means that 3t squared minus 3 must equal 0. And 2t does not equal 0 there, but let's not worry because none of these values intersect each other, right? And so what did we just find out? This means that this happens where t is equal to plus or minus 1. Okay? But it says find the points on C. How do you turn this into a point? Again, create your little chart, right? So here's -1, here's +1. What would they actually be as points? Well, we're going to use the original equations for that, right? So remember, x is equal to t squared, so x is equal to 1. I'm going to put a 1 right there. And remember, y is equal to t cubed minus 3t. Oh, so it's -1 cubed minus 3 times -1. What do we get here? We get -1 plus 3, it's +2, and so our y value is 2. Okay, Now, what about for the other t value of 1? T value of 1, we get x is equal to 1 squared, which is again 1. Y is equal to 1 cubed minus 3 times 1. So that's 1 minus 3, that's negative 2. So we have a horizontal tangent line at the points 1, 2, and 1, negative 2. We're not done because they want also vertical tangent lines, okay? But this is at least half of our answer here. Okay? Now, what about vertical tangent lines? Remember, vertical tangent lines are going to occur whatever t value makes this thing approach infinity or negative infinity. So for the vertical tangent lines, we're going to study t equals 0, right? Because this is the point where dx dt was equal to 0 there. What is the limit as t goes to 0 from the left or the right of our curve, or our tangent line? Sorry, we had 3t squared minus 3 over 2t. So if you approach 0 from the left or the right, what's going to happen here? On the top, what do we get? Becomes negative 3, and the bottom is going to be 0. Remember, we're approaching 0 from either direction, but that's okay. We know that this goes to plus or minus infinity. Which is which depends on which direction you are coming from. But that's okay. As soon as you get infinity, you're good. This means that we have a vertical tangent line at what point? Well, 0 is the key value here. Zero. So if you plug in 0 into your parametric curve, we get x equals 0 squared, which is 0, so x is 0, and y is equal to 0 cubed minus 3 times 0, which is 0. And so we have a vertical tangent line at 0, 0. So far, so good, right? We've got all our vertical tangent lines and all of our horizontal tangent lines. So we're going to move on now to part C. Okay, part C asks, determine where the curve is concave up or concave down. Okay. All right, so let's go ahead and do these one at a time. We need to figure out where the second derivative is positive and where it's negative, right? So I want you to recall concave up is synonymous with the second derivative with respect to x being positive, and concave down is synonymous with the second derivative being negative, okay? This is something that we learn in Calculus 1. Okay, so we need to figure out what the second derivative is. So remember, the second derivative, we are going to take the derivative of the first derivative with respect to t and divide it by dx dt. What is the derivative of dy dx with respect to t? Well, let's do that over here, okay? Remember, dy dx was equal to 3t squared minus 3 over 2t. So what would be the derivative of that guy with respect to t? It's going to be the quotient rule, right? So it's going to be the derivative of the top times the bottom minus the top. Let me back up here. I need more space. Not going to be enough room. So let me let me back up. So the second derivative of y with respect to so I have the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. What do we get here? This is equal to 12t squared, and then minus 2 times that. So that's minus 6t squared, and then plus 6 over 4t squared. Or this is the same as 6t squared plus 6 over 4t squared. We can actually factor this. It looks like this. I'm sorry, I could take out a 6. Well, let's think of it this way. If I take out a 6 and then cancel it with the 4 at the bottom, I actually end up with 3 times t squared plus 2 over 2t squared. Now remember, this is just the numerator here, right? So if I were to block this off, this is just the numerator, 3 times t squared plus 2 over 2t squared, and I'm dividing it by dx dt. Remember dx dt, we did that on the page before, right? Dx dt is 2t, right? Dx dt, where is it? There it is, 2t. So if I divide it by 2t, that ends up just getting multiplied by the denominator, and so for my second derivative, we get 3 times t squared plus 2 over 4t cubed. Now you'll notice that this only can equal 0 or undefined at t equals 0 is the only critical point that we have to worry about here. And so if this is 0, if we plug in anything to the right of that into the second derivative, let's write second derivative here, right? So if I plug in anything bigger than 0, you notice that you get a positive number, right? So let's say, like, for example, if you plug in t equals 2, you get a positive, right? So that means that everything beyond 0 is concave up. And if you plug in something negative, the top is always positive, but the bottom is going to be negative then, and this is concave down. Okay? So let's go ahead and write the results on the next page. The curve is concave up when I'm going to write when t lives from 0 to infinity, and concave down when t lives in negative infinity to 0. Okay, so there you go. We finished part C, and so part D says to sketch the curve. Okay, we now know a lot of information, so we should be able to sketch this curve without much of a hitch, okay? So let me draw a picture here of our coordinate system. So this is my coordinate system. This is x and this is y. Now I'm going to plot some points here that we have, okay? First of all, remember that we found out that there were 2 tangent lines at 3, 0, right? So we know that we're going to cross 3, 0 2 times. So here's 3, 0. We know that we're going to cross it twice, once when t is negative root 3 and another when t is positive root 3. Okay, we also know that at t equals 0, we had a vertical tangent line. Let me go back to the information that we know, right? We know we have a horizontal tangent line at the points 1, 2, and 1, negative 2. So 1, 2 right here, and 1, negative 2, that's right here. What else? We also know that we have a vertical tangent line at 0, 0. So I'm going to put a point here. Okay, so what happens? When we have a horizontal tangent line, I'm going to put little dotted line up here. We know that we're going to have horizontal tangent lines there. And we know that root 3 and negative root 3 is the slope at 3, 0. So we know that at a certain point, it's going to look like that. And at another point, it's going to look like that. Okay. So let's think. At t equals negative root 3, if we come back. Okay, so first at t equals negative root 3, we actually hit this guy, right? We have a slope of negative root 3, okay? What that means is that it starts coming this way. You notice I did concave down that whole time. And I stopped there because that's where t is 0, because at t equals 0, we're at 0, 0. And now concavity changes up. So this is what the curve looks like, and it is going this way, right? Because these are increasing t's, right? This is, we start off here at t equals negative root 3. Then this is t equals negative 1. And then here t is 0. And then here t is 1. And then here t is also root 3 the second time it hits this point. So there you go. We were able to sketch the curve. We need to let go of our notion in the past that we always have a function. Notice here that y is not a function of x. This fails the vertical line test, right? So a curve like this could only be described parametrically. Okay, let's try another example. This was a good example. Let's try another one. This one will be a lot shorter because we're not going to go through the whole concavity mess and all that stuff. So let's start with, this is actually another three-parter. So first part A, I want us to find the tangent line to the cycloid. X is equal to r theta minus r sine theta, and y is equal to r minus r cosine theta. Remember, r is fixed. It is not a variable, right? So theta is the parameter. And all of this is going to be, so find the tangent line at the point where theta is equal to 2 pi over 3. So let's do part A first, okay? We're going to start by taking the derivative here. So the parameter here is theta, so this means that dy dx is just going to be dy d theta over dx d theta. So what is dy d theta? Well, remember, r is a constant. So the derivative with respect to theta of y is just going to be r sine theta on the top. And the derivative of x with respect to theta is r minus r cosine. Sorry for the interruption here. The derivative of y is r sine theta. The derivative of x with respect to theta is r minus r cosine theta. Okay? All right. So, by the way, we notice something interesting. All of the r's cancel out, so we just end up with this. So, at theta equals 2 pi over 3, let's see what we get for the slope. So the slope that they're asking us for, we want dy dx at theta's equal to 2 pi over 3. So what do we get when we plug 2 pi over 3 into that? We get sine of 2 pi over 3 divided by 1 minus cosine of 2 pi over 3. So what would sine of 2 pi over 3 be? That is root 3 over 2 over 1 minus cosine of 2 pi over 3. I know that's going to be a negative, and I believe it's negative 1/2. So this is equal to root 3 over 2 all over 3 halves, which ends up being root 3 over 3. Okay, so there we go. We got ourselves the slope. That is, they wanted the tangent line, so we're not quite done yet. We do need a point for this, right? So what would be the point associated with this? So here's our theta, here's our x, here's our y. I'm going to do a little chart here. So what happens when theta is theta is 2 pi over 3. So what would x be? So x would be r times 2 pi over 3 minus r sine of 2 pi over 3, which is root 3 over 2. Okay? And so that would be r times, what would we get here? 4 pi minus 3 root 3 all over 6. I'll write it like this. That's our x coordinate. Okay, sorry, that whole thing does not fit in that little chart I wrote down, but that's okay. Y is going to be r minus r cosine of 2 pi over 3, which is equal to r minus r times negative 1/2. That would be r plus 1/2 r is 3/2 r. Okay? And so this guy right here, all of this is our x coordinate. So if you think about it, using our slope, our point slope form of a line, this would be like your x naught, and this would be like your y naught, right? And so what would the tangent line be? Tangent line at theta is equal to 2 pi over 3, right? So we got, remember, it's y minus y naught is equal to m times x minus x naught. And so this is going to be y minus, what was our y naught? So our y naught was 3/2 r, right? Is equal to, let's go back here, we got root 3 over 3 times x minus x naught. What's x naught? It's that whole thing that I pointed to there. So this is going to be r over 6. So I'm going to distribute there. I get minus 3 pi r over 2. So let me go ahead and distribute here because I think it'll look nicer in our equation. So this is equal to 3 pi r over 2, and then minus, it's going to be 3r root 3 over 6, or r root 3 over 2. Right? I think it's over 2. Ah, okay, I see my mistake. Sorry, guys. That's what happens when you do problems on the fly, right? This is 2 pi r over 3, and this other guy is r root 3 over 2. There we go. So all of that is x naught, so I'm going to subtract that. So it's minus 2 pi r over 3. And then I'm subtracting the second guy, which makes it a plus, so plus r root 3 over 2. And yes, we could do some simplifying there, but I'm just going to leave it alone, okay? This is going to be how I leave my answer. Okay? So this is my tangent line at theta equals 2 pi over 3. Okay? All right, let's go to part B now. Part B asks, at what points is the tangent line horizontal? So at what points is the tangent line horizontal? Well, okay, let's go back to our derivative, right? So we know we have a horizontal tangent line occurs where dy dx is equal to 0. So we need to see where it's 0, dy dx. Let's remember, we've got our dy dx here. dy dx, dy dx is sine theta over 1 minus cosine theta. So where is sine theta equal to 0 and where is 1 minus cosine theta equal to 0, right? Because remember, dy dx is equal to sine theta over 1 minus cosine theta. So sine theta is 0 precisely where theta is equal to any multiple of pi. So let me just say n pi, where n is an integer. Now, what about 1 minus cosine theta, though? We have to be careful. We've got to make sure that we're not dividing by 0, right? So where does 1 minus cosine of theta, we want that to not be 0, right? That's the only way we could have a horizontal tangent line, is if the top is 0 and the bottom is not. Otherwise, you'd have 0 over 0. So this means that the only place that cosine can be 1 is at multiples of 2 pi. So this is when theta is a multiple of 2 pi. So I'm going to write 2 pi. Let me write it this way. Yeah, I guess that's good, actually. So in other words, we want theta to be a multiple of pi, but we don't want it to be an even multiple of pi. So this actually means that we want theta to be an odd multiple of pi. This is where we have a horizontal tangent line. Okay? So this is a really interesting case, right? And does this case actually make sense? I'm actually going to show us, or I'm going to show you guys what that looks like on the picture of the cycloid, so you could see that this all makes sense, okay? So they wanted to know at what points is the tangent line horizontal, so we should probably go ahead and figure out what points those are, right? So what do we get for x? Remember, it's r theta minus r sine theta. So it's r times theta minus r times sine of that. Well, what's sine of any odd multiple of pi? Sine of any odd multiple of pi, it's going to be 0, right? Because sine of pi or 0 or 2 pi or 3 pi, sine of any multiple of pi is 0. So actually, this is going to be 0. So this is just, I'll put the odd number first and then times, let me write it this way, pi r. So that's x, and then y is equal to, remember y is equal to r minus r cosine theta, right? But what's cosine of any odd multiple of pi? It's actually -1, and so this ends up being 2r. Okay, so horizontal tangent lines occur at 2n plus 1 pi r, and then 2r, where n is any integer. These are the points. Okay? I'm going to draw a picture of this. Don't worry. Okay? Now, what about vertical tangent lines? Well, vertical tangent lines are going to occur where the denominator is 0 and the top is not. So let's see. This means, so vertical tangent lines could appear where, remember, we have this. We want to know where this thing goes to infinity, right? Where does that thing go to infinity? Well, how about we check first where theta is an even multiple of pi, right? Because that makes the bottom go to 0. What about the top? Okay, well, if the top is 2n pi, it doesn't matter what n is, right? If the top is an even multiple of pi, that's also 0, and so this leads to 0 over 0. So what we actually need to do is we need to do a limit, right? We need to know what the tangent line is approaching. So what's the limit as n goes to? We can go to any multiple of pi here, right? So just to make life easy right now, or sorry, I shouldn't say n, let me say theta, right? Let me just say that theta goes to 0, and I want you to recall that the cycloid looks like this. It keeps doing this forever, right? So what we're doing is we're checking if that's the coordinate axis. If this is the coordinate axis, then we're checking right in this first thing at the origin. And if there's a vertical tangent there, there's got to be one everywhere, right? So there's got to be one at every one of these little humps. So let's check the limit as theta goes to 0 of sine theta over 1 minus cosine theta. So if you let this go to 0, we know that this is equal to 0 over 0, so we're going to use L'Hopital's rule. And so this is going to equal the limit as theta goes to 0 of cosine theta on the top, and the bottom is just going to be, well, its derivative is sine of theta. And if you let this go to 0, this is equal to 1 over 0. In other words, it approaches infinity. Now, of course, it's going to be a positive or a negative infinity depending on what side you come from, but that's not what's important. The important thing is we know we have a vertical tangent line at 0 and hence at every multiple of 2 pi. Okay, so what do you get at those multiples? Well, we could plug it into the curve, or we could remember that every single time that this thing rolls around, it's 2 pi r, right? So this is going to be 2 pi r. This guy is going to be 4 pi r. This is going to be 8 pi r. And this is going to be, 6 pi r. And so on, right? So we're ready to write that down. We've got a vertical tangent lines at the points 2n pi comma 0. Right? And that's exactly all of these. These all give you a vertical tangent line. Okay? And let me go back and actually show you where the horizontal tangent lines live. Remember, we said it was at odd multiples of pi times r, comma 2r. Well, an odd multiple of pi times r is actually right here, and then 2r is actually this exact height. It's right at the top. So you notice that is a horizontal tangent line. Horizontal tangent line. Horizontal tangent line. Right? Because this height is 2r. Because the height halfway through is r. The radius of the circle, right? Okay, so this shows us that every tangent line occurs at an odd multiple of pi odd multiple of pi times r, comma, 2r. This one would be 3 pi r, comma, 2r, and so on, okay? That's where all of these horizontal tangent lines are. So this example has taught us a little bit about the cycloid. All right, so now that we are a little bit comfortable with tangent lines, we're going to move on to the next part of the section. This is a long video, I apologize, but there is a lot going on in this section. Now we're going to talk about areas under curves. So now that we know how to deal with derivatives, we're going to learn how to do a bunch of stuff that we've been doing in calculus. We're going to learn how to do it with parametric curves. And of course, let's start with areas under curves. So I want you to recall, I guess we haven't done areas under curves for a while, but remember from Calc 1 that if y is equal to a function f of x, then the area under f of x from x equals a to x equals b is this, right? This is area. I mean, this is, in fact, the definition of a definite integral, right? Was the area under a curve. Okay? But remember, this is the same. We could have learned it this way, right? We could have learned this notation. Now, if y is equal to y of t, right? If y is a function of t and x is a function of t, and t goes from alpha to beta, then what would this become? Okay. This would become now the integral from alpha to beta, and y would become y of t, and then dx, well, dx would just be x prime of t dt. Okay? What this is saying, by the way, is that we're still going with our formula y dx. It's just that dx is now x prime of t dt, and y just becomes y of t, right? You just write the function of t that's there. Okay, so it's really just the old formula. We're just translating into the parametric equation. So let's go ahead and try an example here. This is number 3. Let's do something interesting. Let's find the area under one arch of the cycloid. Okay. All right, so remember, x is equal to r theta minus r sine theta, and y is equal to r minus r cosine theta. And we're trying to find the area under one of these arches, right? Let's draw an arch here. An arch looks like this, okay? We're trying to figure out what the area is under one of those. So what do we think? What's going to happen? Well, I want to figure out what dx is, because remember, the area is equal to y dx, okay? Well, we already know what dx is. Dx, we took its derivative before. It's r minus r cos theta, right? And so this is going to be the integral, and we're going to put the y in there, r minus r cosine theta. That's the y. And then dx is r minus r cos theta. It's actually, we get the same function, don't we? Interesting. So we could pull out r squared here. And we're left with 1 minus cos theta times 1 minus cos theta, which is really 1 minus 2 cos theta plus cosine squared theta d theta. Now, we never did say what theta goes from. I should do that now, right? Remember, when theta goes from 0 to 2 pi, that gives us a whole cycle here. But I'm going to go from negative pi to pi. Okay, that still should work, right? So, what do we get? How do we do this integral? Well, remember, cosine squared theta, remember we can use half angle on that, and that's 1 plus cosine 2 theta all over 2. Okay? And just to save time, I want to go ahead and write the answer because I know you guys know how to integrate this. We end up with the answer 3 pi r squared. And how does this make sense geometrically? This is actually quite interesting. What this is saying is that when you take this circle, this is of course not drawn to scale, but what this is saying, let me try to draw this a little bit better, okay? So what happens is if you have, let's say, a circle and you roll it along, right? What we're saying is that when you roll this circle along and it traces out this curve, the area of the circle is pi r squared, and then the area under the whole thing is 3 pi r squared. So interestingly enough, when you roll this along and the dot goes around 1 full revolution, you have actually tripled the area of the circle exactly, which is crazy. It's weird that it works out to be exactly 3 times. The book actually says that Galileo guessed this way back in the day before it was actually proven, but it was proven later on by a French and Italian mathematician at the same time. So very interesting historical fact regarding when this was actually discovered. Okay, so that's how you find the area under a curve in parametric equations. What about arc length? Okay, what about arc length? So I actually want to jump straight into what we get, okay? Now, remember, we've learned in 8.1 that the arc length is equal to the square root of 1 plus dy dx squared, right? A to b. But now let's manipulate this so that, and we had a dx here, right? Let's manipulate this now so that this looks like something that we can work with. Remember, we have parametric equations, x of t and y is equal to y of t, okay? Remember, dy dx is really, because of our formula, we know that that's dy dt squared over dx dt squared. And we know that dx, by what we did in the last problem, is dx dt times dt. But if I put this guy inside the radical and distribute it to both, it becomes squared. And so here's what we end up with. We then integrate from alpha to beta, remembering that t goes from alpha to beta. And this is going to become dx dt squared plus dy dt squared dt. So this is our arc length formula, which is actually I think it's pretty easy to remember. You just take both derivatives, you square them, you add them, and you take the square root, okay? And that ends up giving you the arc length. Another way to remember this is, remember we had that dx squared plus dy squared is equal to ds squared? Well, this actually leads to dx dt squared plus dy dt squared is equal to ds dt squared. And so we can also remember this formula by remembering just the integral of ds, and remembering that ds is really all of this, okay? So ds is really the square root of both of these, and then dt. So if you ever forget the formula, you always know that this is the arc length formula, and essentially you're doing this. And then this can be found by taking that. Okay? All right. So let's go ahead and try an example here. Some interesting examples. Let's find the circumference of a circle with radius a. Remember, a is a constant, okay? So just to remind you that it is not a variable in this problem. Okay, so the trick first is let's parametrize the curve. Let's parametrize the circle. So we need to write x and y as functions of a variable. Remember, we actually learned how to parametrize these in the last section. A circle with radius a, we can write x is equal to a cosine t, y is equal to a sine t, and that gives us the circle. But t goes from 0 to 2 pi, or I can write this as negative pi to pi, and this gives me the whole circle. So dx dt is equal to negative a sine t, dy dt is equal to a cosine t. So the length is equal to the integral from negative pi to pi of the square root of dx dt squared plus dy dt squared. But everything under here is just a squared, because the sine squared plus cosine squared gives you 1. And then the square root of that is a. So you could pull the a out, and you're actually going from negative pi to pi just dt. And so this becomes 2 pi a. So very interesting. We got the formula for the circumference of a circle, right? Because you guys already knew that the circumference of a circle hopefully is, 2 pi times the radius. Well, now we just derived it ourselves, which is pretty neat. The integral ended up being very easy to do, right? Let's do another one. How about this time? I'm not going to actually solve this. I just want to set up the integral just to save time. Let's set up an integral that can be used to find the length of one arch of the cycloid. Remember the cycloid formula? Let's write it down. R theta minus R sine theta, and y is equal to R minus R cosine theta. Okay, well, we already have dx and dy, right? We've taken these derivatives before. Remember, dx d theta is equal to r minus r cosine theta, and dy d theta is equal to r sine theta. So the length is going to equal, remember, theta goes from 0 to 2 pi, and that's going to give us one arch, okay? So 0 to 2 pi, and we're going to take the square root of, and then we're going to square these both. If we square dx d theta, we end up with r squared minus 2r squared cos theta, and then plus r squared cos squared theta. All of that is dx d theta squared, and then plus r squared sine squared theta. If we pull the r squared, actually let me go ahead and add these two together. These two add up to just r squared. We can combine it with the first r squared, and this gives us 0 to 2 pi, and the square root of, I get 3r squared minus 2r squared cos theta d theta. Okay? Okay. Now what? Oh, sorry, I don't know why I put a 3 here. That's 2, isn't it? Yeah. There we go. That's better. And I know I can pull out a root 2 and I can pull out an r squared. And so really, here's what we get. Because I pulled out a root 2r, and I'm left with just 1 minus cosine theta. And I will leave it like that. I just wanted to set the integral up, okay? Okay, there is one last thing I want to talk about. I'm not going to do examples here, but I just want to talk about the surface area now. Surface area of a solid of revolution. So this is almost like 8.2 again, except we are doing parametric, okay? So I want you to recall that when we revolve about the x-axis, our formula for area was 2 pi y ds, right? So all we have to do is translate that into our new language, okay? This is going to be 2 pi times y of t, and then ds, remember, is going to be dx dt squared plus dy dt squared, and then dt, and alpha to beta. So that's what you do when you revolve it around the x-axis, and now when you revolve about the y-axis, remember that means that the area is equal to the integral of 2 pi x ds, and so this is going to be the integral of 2 pi times x of t, and then the square root of dx dt squared plus dy dt squared, and then dt. What's nicer about this and then in 8.2 is that, remember, you still had to choose between which variable to integrate with respect to. Was it easier in terms of x or in terms of y? But here you don't have any choices like that to make. At the end, all integrals will be in terms of t in any parametric problem. Now, of course, or theta or whatever you call your parametric variable, but the point is it's always going to be in terms of the parameter, never in terms of x or y when you're doing this. Okay, guys, I'm not going to do any examples of the surface area ones. You could see one in the book, but really the whole point here is to learn how to do these tangent lines, slopes, and then how to translate all these old equations into our new parametric language. Thank you very much for watching. I hope the video was helpful.